Hi, welcome to my channel. Today, let's try to solve this problem. First, missing positive. Given an unsorted integer array, return the smallest missing positive integer. And we have to implement this problem in O of n time and with O of 1 complexity. So, let's try to forget about this time complexity and space complexity requirement. If it's not there, how we would try to solve this problem? We need a first missing positive number. So in this example, if you see, the first missing positive number is 3. In the second example, if you see, the first missing positive integer is 2. 1 is there, 2 is not there, 3 is there, 4 is there. Now here in the third example, 1 is not there, so yeah, 1 we have written. So if you don't have any time complexity and space complexity constraint, how we would solve this problem? We would traverse through all the numbers. If you see here, the length can be up to 1 power 5. Okay, we will traverse to 1 2 3 4 5 6 numbers. We'll traverse from 1 to 2 power 5 numbers, 10 to the power 5 numbers, and see which number is not present in my array and return that. 1, I'll check all the numbers that is present in the array. 2, I'll check all the numbers present in the array. 3, I'll check all the numbers present in the array. If 3 is not there, I'm returning like that. Okay, here what would be my time complexity and space complexity? Space, I'm not using any extra space. What is the space time complexity here? Time complexity is for each number from 1 to n. Let's consider n is the last number. For each number from 1 to n, we are traversing all the elements present in an array. Okay, that would be O of n square, and space complexity is O of 1. We are not using any space complexity. Now what if we have time constraint, but we did not have, let's consider only time constraint for now, that we should do it in O of n time, and we did not have any space complexity. We did not have any space complexity constraint. In this case, what you do, in the first approach, what you are doing, we are trying to traverse all the elements and checking if it's present or not, right? I want to optimize that, searching if the element is present in array or not. To optimize that, what we can do, we can store that in an hash set, so that checking if the number is present in an array would be a constant time. Yeah, so in this case, what I would do, first I would traverse all the elements present in an array and store it in a hash set. Okay, now I will traverse from 1 2 3 4 5 6, like up to 10 to the power 5 numbers, and see if that number is present in that hash set or not. If that number is present in a hash set, I'm continuing with my search. If that is not present, that is my solution. Okay, now what now if I'm considering this here, what is the time and space complexity here? Time, we are reducing it to O of n. We are traversing all the elements once, and we are traversing one from 1 to n one more, so it is O of n. The space complexity is not constant. We are using extra hash set, which has some O of n of space complexity. Now I want to consider time and space complexity both, that is required in the question. Now here what we can try to do is, instead of using an extra hash set, why not I use my integer array only as a hash set that I have, right? I have an array, I will use that only as my hash set. Like I have 0, let's say I have a number 1 to 5 in an hash set. The index would be 0 1 2 3 4. Okay, and my numbers are 1 2 3 4 5. 1 is there in, I'll use the index as the key, and what I'll try to do, I'll try to map the index with that particular key. Let's say I have 5 4 3 2 1. Let's say I have a number as 5 4 3 2 1 in my array, and my indexes are 0 1 2 3 4. I will try to bring all the numbers in an particular indexed form, and I'll traverse to that array and see if the index is matching with that key or not. If it is matching with the key, I'm not concerned with that. If that index is not matching with whatever key that is present in an array, then that indexed value is my solution. That index is the solution, right? That is I plus 1. I'm considering the indexes as 0 index array. Yeah, that's why it's I plus 1 the index. Okay, now here we can see then the array can have negative numbers, as well as the numbers can go up to the power 31 minus 1. So what you do, what is the maximum number that our hash map can store? That is n. That is n is the length. The length is the maximum number that our hash map can store, and the missing number would definitely be within that n, right? If the size of a length is array n 0 to n, the missing number would be either within that nth number or it is n plus 1, right? Yeah, the same concept we are trying to use it here. I'm trying to, first what I'm doing, I'm traversing all the way n. If the ith number, if the ith index, the number that is present in the ith index is matching with the index, is matching with the element at that index, I'm not caring it. I'm not caring, because that number is already present in its position, in its correct position. I'm not caring. And let's say if the number is negative and the number is greater than n, then also I'm not considering, because the number that we need is within the length, within the uh, within 0 to n numbers. Okay, and what I'm doing, I'm now, these two conditions are done. Now I'm taking the index 1 index element, and I'm taking the value of that element, value of that number or that particular index. I'm seeing where that element belongs to. See, this is the index, I'm checking, and I'm checking, this is the second index, that is where the element at my ith index belong to, that I'm checking. If the element at my ith index and where that element has to belong to are same, that means, let's say at index 1 I have 5, and at index 4 also I have 5 number, both are same, so swapping that does not make any sense, right? There is definitely some number missing. That's why there's already a number which is missing, and that missing number is filled up with that number. That's why so that case also we are neglecting, and we are neglecting that case. And if they are not equal, we are bringing that ith index to a particular, to the right value, right? Let's say my ith index is 1, and if the element at my ith index is something other than 1, I'm bringing that 1 to my place, to that particular place, and that's what it's happening here, right? Index 1, index 2, ith 1 is let's say this is 5, I is 1, now it has to go to 5, and I'm moving that 5 element to the 5. I'm just swapping that numbers, I'm bringing the right element to my place. Okay, now after creating that hash map of an array, what I'm trying to do, I'm traversing to that array again, that hash map, and seeing if the if at ith index, if the element that is not there is not equal to I plus 1, then that element is the missing one, right? That element is the missing one. If it is not, if it does not find any such element, then the first missing element would be n, the size plus 1, right? So here we discussed three solutions. Yeah, what is the time and space complexity of this approach? We are traversing, we are preparing the set, which is linear time. We are making use of the existing array only as our hash set, so we're not using any extra space here. Okay, and the time complexity is also linear. Okay, so we discussed three solution. One is normal brute force solution, where we, for each element from 1 to n plus 1, we are checking if that is present in array or not. We are returning that element. Here in approach to optimize the existence of a number in an array, we use an hash set, where we are using extra space, which is leading to O of n of space complexity. Now the third approach is me making use the existing array only as our has set kind of a thing, where we bring the number to this actual hash position, that is where to its indexed position, and at the final we traverse to that same array and see if that index position has the corresponding number or not. If it is there, then we are moving forward. If it is not there, and that will be the missing number, right? Thank you.